Hey everyone, today is part 2 of describing features of functions, and really today we're going to be focused on the information that we can get from the second derivative. So everything we did yesterday around increasing and decreasing was driven by the first derivative. Today when we work with concavity, which you've had an introduction to, that's really going to be driven by the second derivative. So before we get into how we use that derivative, I want to do a quick review. Remember, concave up we said was where we're kind of opening up like a cup. Okay, and we know from what we did with linear approximations and determining if they were under or over estimates, we know we're concave up when the second derivative is greater than 0. So let's go ahead and look at different scenarios and figure out how we're going to figure out intervals where we're concave up. Now, when we're given a graph of f, it's a little bit tricky to determine this, so we always kind of estimate. But I'm looking for where my graph is opening up. So in this case, I would say it's about here. That part would hold water. So we'll say that f of x is concave up on the interval from, it looks about 1 to infinity. Now, the good news is we don't really ever have to give information just looking at the graph of f because it is kind of an estimating game at that point. Now, let's see when we look at f prime. So we said we know we're concave up where f double prime of x is greater than 0. Well, I know that f double prime of x is greater than 0. That means if I'm looking at the graph of f prime, I need to know where the slope of f prime of x is positive. Or in other words, where is f prime of x increasing? So in other words, to say this again, right, we know that the second derivative is greater than 0, where the slope of our first derivative is positive. Right? I know the slope of my first derivative is going to give me that second derivative, and I'm looking for where that's positive. So I'm going to have a positive second derivative wherever my first derivative is increasing. So again, I can see here, I'm increasing on this interval here. So I could say that f prime of x is, let's start again. I'm analyzing f, so I know that f is concave up on the interval from 1 to infinity because f prime is increasing, which means that f double prime is greater than 0. Now, if I have the function, I know again, I'm looking for where that second derivative is greater than 0. So the first thing I have to do is find that second derivative. So I know my first derivative is going to be equal to 6x squared minus 12x. My second derivative is going to be equal to 12x minus 12, and I want to know where that's equal to 0. So if I factor out a 12, I'm going to have 12 times x minus 1 is equal to 0. So I know I'm interested in what's happening around x equals 1. So now, similarly to what we did with increasing or decreasing, I'm going to go ahead and set up a table here. I know I have my endpoints are kind of negative infinity to infinity, not endpoints. I have an open interval here. And I'm looking at what's happening around 1. So if I look at a point in this interval, let's say negative 1, if I plug that into my second derivative, negative 1 minus 1 is a negative 2, so that negative times a positive is going to give me a negative. If I plug in something between 1 and infinity, say 2, 2 minus 1 is a positive, times a positive is going to give me a positive. Again, we know we're concave up where that second derivative is positive or greater than 0. So we would say that f is concave up on the interval from 1 to infinity because f double prime of x is greater than 0. So now concave down is just going to be the flip side to all this. So concave down, again, remember graphically for our function, looks like this. We said it looks like a frown. And that's happening where f double prime of x is less than 0. Now in this case, again, we're estimating on the graph of f of x, but I'm definitely concave down about over that interval. So we would say f is concave down on the interval from negative infinity to 1. Now again, here we have the graph of f prime. So I know that the slope of f prime is going to give me information about the second derivative. So if I want the second derivative to be less than 0, that means I'm looking for where the slope of f prime of x is negative. So really I'm looking for where f prime of x is decreasing. I know that wherever f prime of x is decreasing is where I'm going to be concave down. So in this case, f prime of x is decreasing over this interval. So you would say f is concave down on the interval from negative infinity to 1 because f prime is decreasing. And again, we would do the same process here. If we had our original function, we would go ahead and find our second derivative, just like we did here. We would find where that's equal to 0, and we would set up our table. So I'm not going to go through that whole process again, but we would have our table here. Now we would be looking for where that was less than 0, which is over this interval. So we would say f is concave down on the interval from negative infinity to 1 because f double prime of x is less than 0. So we have one last term for this video. And here we have what's called points of inflection. So points of inflection are where the concavity changes. So I could change from concave up to concave down, or concave down to concave up. Those points where that change happens are called points of inflection. And here's what we're really looking for. We're looking for points where the second derivative is equal to 0 and the second derivative changes signs. So we'll get into that in a little bit, but we really have two criteria here. A point of inflection is where f prime of x equals 0. If we only know this piece, we only know the possible, and I'm just going to abbreviate, points of inflection. So just finding where f prime of x is equal to 0 gives us possible points of inflection. To know for sure that we have a point of inflection, we actually have to add the criteria that we know f double prime of x changed signs. So let's go ahead and look here. We said earlier that we were concave down on this interval here, and that we were concave up over this interval. So that tells me here that our point of inflection is that point where it changed. So f of x has a point of inflection at x equals 1, and I want to be specific here and be sure to specify that it has a point of inflection there because f changes from concave down to concave up at x equals 1. So we know it's a point of inflection because we know the concavity actually changed there. So let's see how this applies if we're looking at the graph of f prime. So my first criteria here to identify a point of inflection is to check where the second derivative is equal to 0. Or in other words, where is the slope of f prime equal to 0? And I know that's going to happen down here. Now, I also have to check, did that second derivative change signs? So in other words, did the slope of the first derivative change? Since my slope changed from negative to positive, we actually changed, so we know we have a point of inflection. So here we would say f of x has a point of inflection at x equals 1 because f changes from decreasing to increasing at x equals 1. Okay. Now, again, the last part here would be if we were given a function, could we determine where that point of inflection is? So again, this is our same function from before. So we know, again, when we're talking about concavity, we're always looking at that second derivative, which we had was 12x minus 12. And we set that equal to 0. We found out that x was equal to 1, and we made our table. Now, right away here, we wouldn't say we have a point of inflection at x equals 1, because we don't know that f prime changed signs. So we would still make our table. We know we have a possible point of inflection, but until we have that table, we wouldn't be able to verify for sure. So I'm taking our table from the previous page, since it's the same function, and now I can see my second derivative is equal to 0 at x equals 1, and f double prime changed signs. So now we can say that f has a point of inflection at x equals 1 because f double prime of x changes from negative to positive at x equals 1. Now, I'm fairly sure we'll have some questions, so we'll start with those at the start of class, and then, as always, you'll have time to practice and work with this and really see what the AP exam will expect you to do with these types of problems. See you tomorrow.